Hello guys, welcome back to another video. In this video we are asked if the following sums converge or not. If we take a look at those two sums, they're not so common to see, but trust me, they are not so hard to deal with when you get to know the things I will show you now. So the first one, if we would remove the sign, it would look like a classic Leibniz or something. For you people that don't know what Leibniz says, it says that if we have an alternating series, for example like this, and n that is monotonically dropping to 0, for example 1 over n or something, for n greater or equal than n now, this means that from some point it will drop. So it doesn't like in this case, like ln of n divided by square root of n, it's dropping monotonically to 0. So we can apply the Leibniz rule here. This will converge for sure, but we have the sine of 100 divided by square root of n. So what can we do here now? So like the thing with sine, like it's changing the signs and everything, but what we are sure of is that like we can there is one theorem called Abel's theorem, which says that if we like for one, we need to have a series that converges. For example, some bn. This is our bn in this case. That converges, so C converges, and the second condition is that the function we are adding to the series, adding is the series is multiplied with, is monotonic and bounded. So sine, what do we know about sine? Sine is sine here is monotonically decreasing. So sine starting from, okay, you can say like 100 and square root of n for the bigger n, and so on. As n gets bigger, the sine will get lower and it will tend to 0. So this fits our condition that some Cn, for example, must be bounded by something, by some m or something. So this converges and this is bounded. Okay, obviously sine 100 divided by square root of n for big N, this tends to 0, so this is bounded and it is monotonically dropping. So this series converges by Abel's theorem or Abel's test or whatever you want to say. Sorry, that guy was Norwegian, I think. Abel's theorem. Okay, this is done. Okay, when we take a look at the second example, okay, let's put this. At the second example, we see that we have sine of n, cosine of n, arctangent, like a lot of functions there. There is a criterion called Dirichlet's criterion that if we have cosine of n or sine of n, okay, doesn't have sine of x, cosine of x, where the input isn't a fraction, so you can have 1 over x, where input isn't a fraction, and the second condition is that it's divided by a function that's monotonically decreasing. For example, 1 over n. So the series cosine of n divided by n would converge by the Dirichlet's criterion. But we have a lot of functions here going on, so we can't take it right now, let's say. So we need to use some trig identities. Like we will use 2 sine of alpha, cosine of alpha is sine of 2 alpha. Yeah, we have this, we have sine of n, cosine of n. If we divide both sides by 2, we get sine of alpha. Okay, y equals, I don't know, okay, cosine of alpha equals to sine of 2 alpha over 2. So we will apply it here. And this, okay, we will take just 1 over 2 outside, doesn't matter, doesn't have n in it. We will have a sine of 2n, this, okay, what? Fuck. This was weird. Okay, sine of 2n, we have this from this, and we have arctangent of n plus 1 over n or something. Everything divided by ln squared of n. Okay, what is this? Okay, it's better. What can we see here is that now it looks similar to this. Like we have sine of n, sine of 2n, 3n, 4n, 10n. It to all those numbers, I mean sine of n maybe where n is from the integers, we can apply the Dirichlet's theorem or whatever. Dirichlet's theorem. And with the sign we need to have something that's monotonically dropping, and obviously ln to the power of 2 of n is monotonically dropping. So by Dirichlet's criteria, sine of 2n divided by ln of square root ln to the power of 2 of n is converging by the Dirichlet's or whatever the guy's signature is. It converges by Dirichlet's test. And now we are left out with arcus tangent of n plus 1 over n, or tan inverse, whatever you want to say it, call it. So what should we do now? Like we will use a similar thing we used in the previous example we did. In this, like we know that for the Abel's theorem we need something to converge. This converges, and we need the other function to be bounded by something monotonically. Okay, this is m. M is supposed to be like a maximum or something. Okay, it is bounded by something and it must be monotonic. This was monotonically decreasing, and this one, like arcus tangent n plus 1 over n, it's monotonically increasing. So this one is increasing, and you can verify like it is bounded by pi over 2. So by Abel's theorem we have that this converges. And when we add arctangent of n plus 1 over n, it will still remain convergent because the arctangent is monotonic function and it is bounded. So it is completely fine to use the Abel's theorem. So by Abel's theorem, our second example also converges. I think those two examples were pretty interesting. I mean, not that hard when you know the idea behind them, but still cool. Okay, guys, that was it for this video. I hope you enjoyed it. Like, share, and subscribe if you want to see more of this. And see you in the next video. Bye, guys.